Hello everyone, I am Lingam from Singapore University of Technology and Design, and today I will be presenting about our paper titled System Status Aware Adaptive Network for Online Streaming Video Understanding. First, we introduce a preview of the paper. Although there has been great progress in deep neural networks for real-time applications, most existing works do not explicitly consider the general case, where the device's state and the available resources fluctuate over time, and none of them address the impact of varying computational resources for online video understanding tasks. Therefore, we propose a system status-aware adaptive network that considers the device's real-time state, improving efficiency and robustness to fluctuations of the system status. Moreover, training SAN on various types of hardware configurations is not easy, as the labeled training data might not be available or can be computationally prohibitive. To address this challenging problem, we propose a meta self-supervised adaptation method that adapts a policy to new hardware configurations at test time, allowing for easy deployment of the model onto other unseen hardware platforms. Next, we describe our paper in more detail. In this paper, we focus on the online video understanding task, where we make predictions for each video frame immediately by using information in the current frame and potentially past frames. This has many practical vision applications, such as self-driving vehicles, security surveillance, streaming services, and human-computer interactions. However, in practical scenarios, the accessible computing resources of the host devices can be fluctuating and dynamic, since multiple computationally expensive yet important threads are running concurrently. Thus, when the host device is busy with other processes, conducting inference for each model might require much more time than usual, leading to long delays, which could cause safety issues and lagging responses in real-world applications. To address this, we propose our System Status Aware Adaptive Network, SAN, that adapts its behavior according to the video stream and the real-time status of the host system. An illustration is shown on the right. SAN comprises of two components. First, it has a simple yet effective dynamic main network that offers reliable predictions under various network depths and input resolutions. Secondly, it has a lightweight agent that learns a dynamic system status-aware policy used to control the execution of the main module, which facilitates adaptation to the fluctuating system load. The agent can be seen here, and the dynamic main network can be seen here. Specifically, our main network has a dynamic encoder that has both dynamic depth and dynamic resolution. A dynamic depth mechanism gives the encoder the option of producing output features as shallower intermediate layers without having to wait for all the layers to be executed, which effectively reduces the amount of computations required. Secondly, the dynamic resolution mechanism allows our encoder to selectively take in input images at a lower resolution, which also reduces computational costs. These designs are incorporated into a single dynamic network with a total of m times n options, where m is the number of resolution options and n is the number of depth options. The output features from the dynamic encoder are fed into an LSTM that models the temporal aspect of the video. Next, our agent controls the dynamic main network by generating a frame-level processing policy, which basically selects the resolution and depth at each step. To make good decisions amid the fluctuating system loads, our lightweight agent should be both system status aware and streaming input aware. Thus, it takes a system status as input, for example, CPU and GPU utility, as well as an LSTM hidden state for information regarding streaming video input. As for training, our dynamic main network is trained on the specified online video processing task. For example, for online action recognition, the loss can be the cross-entropy loss. The agent is trained via reinforcement learning with a policy gradient loss to maximize the accuracy while maintaining low delay. The formulations for reward and the loss are shown here. Moreover, in various applications, we may need to deploy SAN onto different hardware platforms for online video understanding. However, it is inconvenient to train SAN for each hardware platform, and it might also be difficult to find adequate storage to load the large labeled dataset on all platforms, such as mobile devices, and these issues can be challenging to overcome. Therefore, we further propose a method for deployment time self-supervised agent adaptation, which we call meta self-supervised adaptation. With MSA, we can conveniently train an SAN model on a set of local platforms and perform a quick deployment time agent adaptation on the target device, without the need for the original labeled training data. To solve the challenging problem, we designed two parts for MSA. First, we introduced an auxiliary task of delay prediction, where our agent is now trained to both produce a policy as well as to predict the delay of the selected action. In the figure, we can see that we add another head onto the agent for SAN. Importantly, delay prediction has some connection with the agent's policy, as it is directly related to the system status and the model's computational cost. Another important aspect of delay prediction is that we can conveniently obtain the labels for it on a target unseen hardware platform on the fly by simply measuring the delay of the selected actions during fine-tuning. Therefore, these factors mean that we can fine-tune on the target platform with the delay prediction task. However, we need to bind the delay prediction performance and the quality of the agent's policy. So we use meta-learning as described next. Here, we use meta-learning to train our model such that after fine-tuning on the auxiliary task, which is delay prediction on the target platform, the performance of the agent's policy is improved. First, we denote the delay prediction task as the meta-train task and the agent's policy generation task as the meta-test task. Briefly speaking, there are 3 steps in our meta-learning algorithm. First, we have a pseudo update where we pseudo update our model on the delay prediction task. Then, we test the pseudo updated model parameters on the policy generation task. Lastly, we backpropagate using the meta testing loss to update the initial parameters and achieve our aim of learning a good initialization of the agent, such that after fine-tuning on the delay prediction task, the policy also improves. Please refer to paper for more details. In our experiments, we find that our SAN provides good accuracy and delay for the online action recognition task on the 50 salads dataset. We also evaluate our SAN on sub-JHMDB dataset for online post estimation. Our method also provides good accuracy with much lower delay. We also evaluate the impact of MSA by evaluating on unseen devices. Results on both tasks, online post estimation and action recognition, shows that using MSA gets us close to the fully supervised upper bound and is also more effective than various other baselines. Please refer to paper and supplementary for more experiment results and analysis. This brings me to the end of the presentation. Thank you very much for your kind attention.